How to understand the Haber process. The learning outcomes for this video are: state Le Chatelier's principle and apply it to deduce qualitatively the effects of changes in concentration, pressure or temperature, on a system at equilibrium. Describe and explain the conditions used in the Haber process, as an example of the importance of an understanding of chemical equilibrium to the chemical industry. The flow scheme on this slide shows the main stages of the Haber process. The chemical equation is given at the top. The equation shows a reversible reaction, with the forward reaction being exothermic. Enthalpy change has a negative sign in this case. From the left, nitrogen from the air is combined with hydrogen derived from natural gas into ammonia. The mixture of nitrogen and hydrogen going into the reactor is in the ratio of 1:3 by volume. The number of moles of the gases are in the same ratio. According to Avogadro's law, the reaction takes place under these conditions: a high temperature of about 400 degrees Celsius, a high pressure of 200 atmosphere, and an ion catalyst. The reaction mixture is cooled, so that the ammonia liquefies and can be removed, while the remaining nitrogen and hydrogen are recycled. Think about why ammonia can be liquefied more easily than nitrogen or hydrogen. Revisit the concept of intermolecular forces in chemical bonding. An increase in temperature always increases the rate of a chemical reaction. The Boltzmann diagram accounts for this phenomenon. At higher temperature, a greater proportion of molecules has energy greater than activation energy. Revisit this concept in reaction kinetics if you are unsure. According to Le Chatelier's principle, when a change is made to a system in equilibrium, the system will shift to partially counteract the change. In the Haber process, the forward reaction is exothermic. An increase in temperature will cause a shift in equilibrium to the left, toward the reactants. This is because the reverse reaction is endothermic, and will therefore counteract the increase in temperature by absorbing some of the heat. Therefore, increasing temperature speeds up the reaction that produces ammonia, but reduces the yield of ammonia. If the reaction was carried out at a low temperature to maximize yield, the molecules would not have sufficient energy to react. So the reaction is usually run at about 400 degrees Celsius. This temperature is a compromise between a higher temperature which would reduce the yield of ammonia, and a lower temperature which would reduce the rate of the reaction. Pressure is another factor that will affect the yield of ammonia in the Haber process. An increase in pressure will increase the rate of the reaction, because there will be more successful collisions between reactant molecules. High pressure will cause a shift in the equilibrium towards the production of ammonia. This is because when pressure is raised, the equilibrium will shift to the right to form less moles of gaseous molecules. The forward reaction will use up 4 moles of molecules and form 2 moles of molecules, reducing pressure. In the process, more ammonia is formed and its yield is increased. However, there are high costs involved to build equipment that can withstand high pressure. The favored pressure is around 200 atmosphere, which balances the cost of equipment with profits from increased yield. Adding a catalyst allows a reversible reaction to reach equilibrium much faster. However, the yields will remain the same, as forward and reverse reaction are increased to the same extent. In the case of the Haber process, iron acts as a heterogeneous catalyst, one that is on a different phase from the reactants. Nitrogen and hydrogen molecules will adsorb on the surface of iron, then continue to react and form ammonia. The product then desorbs from the surface of iron. Read the section on heterogeneous catalyst in Reaction Kinetics for more details. Approximately 83% of industrially produced ammonia is used to make fertilizers. All plants need nitrogen to make amino acids, proteins and DNA. Ammonia acts as the precursor to various fertilizers such as ammonium sulfate, which helps to increase yields of crops such as corn and wheat. An important derivative of ammonia is nitric acid. Both nitric acid and ammonia are used in the production of explosives, such as TNT and ammonium nitrate. In 1912, Europe was on the brink of World War I. As ammonia was used in the manufacture of explosives and fertilizers, demand was far greater than actual supply. At that time, most of the world's supply of nitrates came from a giant saltpeter on the coast of Chile. The Allied forces had blocked the supply route and Germany needed a new source. The manufacture of ammonia for production of food and explosives were high priorities for Germany on the brink of war. German scientist Fritz Haber developed the process for the synthesis of ammonia and overcame supply problems for Germany's war effort. He is held by many historians to be responsible for prolonging the war.